We know that Riccati equations, the solution of Riccati equation depend on Q and R, right? So if you have different Q, different R, you get different solutions. So what kind of Q I supposed to have? What kind of R I supposed to have? That's exactly the same question you were asked for the Paul placement technique. What kind of cross-loop Paul I supposed to have? Right? The same question. Because a Q and R, you need to determine, you need to choose Q and R depending on your performance requirement. If I want to have my cross-loop damping, if I want to have my cross-loop system damp out quickly, then I have to choose my R, what? Small, right? Assume Q equal 1. Okay, assume Q is like 1001. So, in real applications, we always assume, well, that's in practice, Q is the identity matrix, then change R. Because Q, this Riccati equation, only relative weighting makes sense. In other words, all right, let me give you an example. All right, that's the simplest example we have is x dot. That's one we use. And we know that we say U equal to FC X, and our J is half X the square plus R U square, right? Did you know that? Remember this one? Right? And I purposely that this is supposed to be Q, my Q. This is supposed to be my R. Then I choose here is Q equal to 1 and R just equal to R, right? For my Riccati equations. All right, now, if I Q equal to 2, if I choose my R equal to my 2R, that's the same thing. Okay. So if you equal to 2 and R equal to R, then you have R just move out, you get the same thing. When you partial it, this constant doesn't change anything. That means only this relative value that you need to consider. So in general, we just net. So in general, we assume, we choose, that's in general. Q is in identity matrix. That's identity matrix. And just value, just change R. According performance requirement.
Performance
So when you apply optimum control, Q, we choose Q is just identity. We just change the R and then check our performance. If our performance is not right, then we change R, the value of R. That's also a square matrix. For single input, R just escape. That's what we do. That's in practice. Of course, you can insist. So I don't want to do this. Yes, that's fine too. But you'll find out that when you vary Q and also change R at the same time, you've got so many parameters you have to change it. That you just get confused. So that's what, in a really practical sense, that's what we do. Now, for example, if you find out that the R you choose don't give you enough damping, then what are you going to do? It is decrease R, right? If you increase R, you don't expect too much closed loop damping. So your R is keep increasing, that means your damping, your closed damping keep down. Understand now? So normally what we do is the same thing. We just optimal control. We design it, then we check our performance. If you design it, performs, you satisfy your performance, that means you have enough damping. Then you say, okay, that's the one I want. But you also have to be careful that when you get too much damping, then maybe you get too much energy. We know that if R decrease, means that we need more energy for the system. Because that means that if that's small, means I don't care much about my energy. You can go ahead, just look at the X. Because I want my performance is very good. I want to drive very fast. That means I have to maybe waste a lot of energy, gas for it. So that's the case. Now, there are another questions you might have. For example, I say if some researcher really gets some different idea. For example, there's another question you might have. Okay. Now, in optimal control. All right. Now, giving AC and BC. All right, and Q and R. Right? Then we will obtain a control gain. Called FC. All right? This is interesting. Then the closed loop state matrix will be AC plus BCFC. Right? That's my closed loop. Agree? Right? Then from here, we have closed loop eigenvalues. Agree? Right? You see? All right. Now let us go this way. Giving these cross eigenvalues, given this crossover eigenvalue then use Hall placement technique to solve for another gain, feedback gain called FC prime. Called FC prime. Alright. Now I'm using the same ACBC. Now I have a crossover eigenvalue derived from my optimal control. Okay. Now I say, okay, I want to use these crossover eigenvalues, but I want to get another gain called, but use Hall placement technique to get another gain called FC prime. I can do that, right? I can do that. Now, I will have, for this, I will have AC plus BC FC prime. And they have the same eigenvalues. They have the same eigenvalues. They may have a different eigenvectors. They may have the same eigenvectors too. Okay, now, which one do you think is better? FC or FC? FC or FC prime? FC. Why? That's optimum only to that sense, the cause effect sense. So, this FC is optimum. We know that optimum. But optimum means we just this. Optimum means we minimize this. We minimize that J, right? We minimize that J. We minimize this. Now the question is, that minimizes, this doesn't minimize anything. Alright? The question is, if I use only crossover eigenvalue here, I may be able to get FC prime with different eigenvectors too, right? If I say, I want to use the same eigenvalue, the same eigenvectors, then FC